All right. Good mornings, and starting on a new chapter. Should have started obviously last week, but Women's Day took that day from us. We will definitely be going a chapter a week for strengths, essentially. So I'll definitely be able to finish this within this scope of time. It's a bit of not a strange chapter, but it gets some students. But I will touch on the. I guess I'll let you know of the necessary tricky ones, which you should be aware of. But I'll have to try and cover all the concepts. Well, I should be able to cover all the concepts today. All right. So the announcement I wanted to make was the first test will be on the 13th of September, on the Monday. So that's basically after the so-called break we're gonna have. I don't. Yeah, this says it's from the 3rd. It's not from the 3rd. Is it from the 3rd? But it's essentially, when is the 3rd? It's the Monday. It's basically like a week off, essentially. I think I should rather say it's this from the 7th or the 10th, maybe. I think that's a more accurate way of saying it here. So let me just start it like that. But I can assure you, it's a daily break because more of a study break, really. Because you'll probably be writing electros the next day, and then thermals on the Friday. So yeah, I'll obviously, once I conduct all those lectures, I'll kind of consolidate that into a small timetable so that you guys are able to obviously have the states. The chapters we're obviously going to be covering, it's for the first four, the chapters we covered in this term. So 3D thrusters, temperature stresses, which we'll be doing today, strain energy, and second moment of area. Okay, is there any questions on this so far? Just so that everyone is aware of this. Yes, Alex.
So you're saying we have probably like a week break or something before we.
Yep, that's correct. Yeah.
Will we be able to ask you questions during that week break?
Yeah, for sure. It's a bit rough for me nowadays because I have like 4 subjects, man. So yeah, I'm probably spending that time sitting up the exams. But yeah, you can ask when you can, just that. I think for the next, what is this, August till mid-September, I'm snowed under essentially. The compound with the marking, so it's gonna hit me bad. It already is. So yeah, no, you can definitely ask, and I'll try to you know answer what I can answer.
All right, thank you.
Okay, cool. So this preparing fact for that week, it's going to be a test week for the mechanical subjects. So I'm just making you aware. And like I said, once I go through all the and I want to inform the other lectures as well, so that they're aware of exactly the test, so we don't all set them all together and make it a bit stressful for you guys. All right, so let's just get on to the formal lecture. Oh, skip the slide. So if you guys had for Stanford Materials 2, I've mentioned that mechanical loading is the essential 5 mechanical types of loads, or what a load is, and this of course is in reference to mechanics of materials here. And we have touched on, of course, the tension load, right? We are aware of that. Induces a direct stress. We've touched on a compression load as well. Exactly the same with tensile load, but also direct stress. And then we touched on shear, so I'm just kind of skipping through that one. We have an idea of shears, two parallel loads acting in under 180 degrees at the phase. And we even touched on the torsion load, which is kind of similar to your shear load, right? Obviously, we just did that for circular sections. So we're going to be looking at vending in not too long, the next 3 or so chapters. And that's another kind of load. And the reason why I'm mentioning all these loads is that these are wherever you look, any system, or in fact anything in life generally, these are the 5 loads. They either happen individually or they're happening in a combination of them. In fact, if you do the next level of strength of materials, you do analysis on the combination of these loads, and you're looking at principal stresses and principal axes. So what's important to note is that these forces or these loading types are always happening all over. And once you're able to identify the loading types, you are able to then conduct the correct analysis for what it is, whether something's in torsion or something's in compression. You know, if you have a column that's in compression, of course, that can be further extended to its bucking. So that's just a special note. But there are these supplementary loads, and of course, I've characterized these loads according to the way I understood them. And someone has some idea, obviously, they saw the pictures, but there are other types of loads as well. It's just not those so-called mechanical ones I'm calling. He also touched on internal pressure. So if you have a pipe, for instance, or even a vessel, the fluid is exerting stress within the pipe walls, right? You also get vibrational loading, right? Something can fall to vibration. And then now what we are touching on is essentially temperature loading, being aware that when our temperature changes, there are stresses essentially induced. And I should have actually mentioned this. We mustn't forget that if there's a force acting upon a thing, it changes the length. It essentially is a strain, and that in essence induces a stress, which is like somewhat of an internal reaction to the applied force. So I wanted to ask you guys, so temperature loading. If anyone has any experience with temperature loading, and also of any other types of loading you can think of. So I actually haven't written them here. I thought I've added them from last year. So anyone has any perspective on temperature loading? Or I'd rather say, has anyone had a situation where something failed because of temperature? And other types of loading. So I'm just giving us 2 minutes for small discussion. Anyone? Alex always has. No, the tests will not be online. I've said all tests are on campus. I stated this clearly start of strength of materials, or in fact all the subjects. So be aware that strictly on campus. So anyone with any experience? Mr. Kawa, using boiling water to clean glass. Can you elaborate on that?
Yeah, if you use boiling water on the wrong type of glass, the glass breaks. Anybody who's cleaned the Oka, so anybody who's cleaned the Oka vase knows what I'm talking about.
Oh, that's fantastic. That is beautiful. Yes, that's a very good case of temperature loading there. Anyone else?
So we had a typical case of one of the motors in for our steering gear stern tube pumps. The key in the shaft actually, I don't even know how to say it, it failed. So it basically wore away, and the shaft was spinning freely within the coupling of the pump, and that got stupidly hot. So it failed due to torsional stress. As soon as that, so what actually happened is that the motor was running, but you were getting no pressure because the pump wasn't turning. So as soon as you open up the pump, you could see it was a failure of basically torsional stress due to heat.
Yeah, that's interesting. Yeah, so that's fantastic. So thanks for that 2 case studies. I think another guy, Mr. Engelbrecht, Shasha, you had any experience with temperature? The last one. Mr. Abril, just under him. Okay, yes.
One more, sir. Do you know what an indicator cock is?
I've heard of it before. Yeah.
It's basically just a little cock on the cylinder heads of the main engines.
Yes, yes.
Which just relieves any of the condensation when you blow through for the engine before you start. One of our indicator cocks when the engine was running was leaking, so exhaust gases was leaking through the indicator cock, and it was actually glowing orange before it failed.
Okay, sweet. That's another one. Yep. Anyone else? Okay. So basically, just this was also to create an awareness of and thanks Mr. Ketzer for his experience and expertise. Temperature, right? Don't just think of something being loaded, tension, compression. There are other types of loading, and I think as an engineer, one must be cognizant of that, especially certain materials, like glass. They essentially brittle, and small temperature loading can immediately rupture them. I mean, even well, it's just not really in this particular one, but steel itself has a ductile, well, ferrous steels or carbon steels has a ductile to brittle to ductile transition, and of course, as the steel gets colder, the steel becomes more brittle. And I mean, if you required we can easily go from 100 odd kilonewtons to like 3 kilonewtons to 5 in terms of rupturing. So I must always be aware of temperature. So this is what we're kind of looking at. When temperature changes, there's additional stress being induced. It's not a lot. Maybe we can tell a quantifying percentage, but we'll see. I'll see how I can play around with it. Okay, just a formal definition. You're not really expected to know this, but it's always kind of important to note. So thermal stress may be considered a stress which developed as a result of a non-uniform temperature distribution within the body. Key, non-uniform, right? It can be normally if it's uniform, it means it's the material has time to kind of it's not sudden. I guess if it's non-uniform, it's too big. It can quickly break or rupture. Examples of this would be parts of an engine. Yes, furnaces, metal cutting machines, rolling mills, plastic molding, extrusion, air compressors, hydraulic and pneumatic devices. So that's obviously we have non-uniform temperature. So this is now kind of important. And so as the metal is heated, and this is I guess the notation we will be using. I don't know if some people know. So if you heat the metal, it's going to expand. So there's an increase plus in elongation. If it's not restricted, right? So that's also key. That NB there, it's key. So just remember, as we heat it, it will expand if it's not restricted. The dimensions will grow, but then no stress will develop in the material, right? However, if we have to restrict, and this is obviously, of course, we're touching on this in the next, just like the next subsequent slide. If you restrict that, that's when stresses are induced within the material. So keep that small statement in your head throughout the lectures now. And also, I just kind of stole this from some book. I think it was an old piece of literature. I'm going to type this over. It said the naval architects principles in 5 aspects of temperature stresses. Temperature gradients in the hull, yes. Deflection in the hull girder due to thermal expansion. Thermal stresses in the hull structure. Buckling of the hull plating. Contribution of thermal stresses to brittle fracture. That's number 5 was what I was talking about. So of course, this is more. Of course, you guys don't really design structures, but be aware, right? I mean, and funny enough, not even talks about temperature stresses because it's a bit small. But of course, temperature structures coupled with fatigue, it's a whole other game there. Yeah, so we're talking about stresses and this and that. Here we have a new guess, I would say, property of materials. It's called the temperature coefficient of materials. I myself haven't done an experiment. I'm getting these expansions, so I'm taking the word for what they have is correct. So just reading off, different materials change dimension at different rates. Yeah, of course, when subjected to temperature changes. Most materials expand with increasing temperature. Yes, some even contract. but some virtually stay the same size. So the coefficient of thermal expansion governs the thermal deformation or elongation in our case, and thermal stress experienced by a material. So this is an important parameter obviously we'll be using. It's denoted alpha. And it also states there the property of the material that indicates the amount of unit change in dimension or the unit change in temperature, right? Lowercase letter alpha, yes. Units not a big deal. It's just 1 over degrees Celsius to the power -1. Am I missing something? But yeah, units not really important. You never really touch on the units anyway. So on my right, you have some. What is this? Some coefficient of expansions. So we're looking at some steels. So they're from some metals, plate, glass, wood. So we look at steel, we've got 11.7 times 10 to the -6. By the way, always the magnitude of 10 to the power -6, just making you aware. Looking at structural steel, we've got 11.7, always around 12. That looks legit. Your stainless steel around 16, so they expand faster. So that's also, I think that's also important to note this coefficient, so that if you ever, excuse me, just take a sip of my coffee then before it gets cold. Now, if you ever know, like if something will expand faster than other one, like even when you're doing welding, for instance, that's a very classical case of temperature stresses. Certain things expand faster and certain metals expand faster than other ones. So if you look at your non-ferrous counterparts, they typically have, which is aluminium, brass, bronze, copper, magnesium, they typically have higher thermal expansion coefficients than your ferrous metals. Obviously, that's probably due to its material science, a lot of material science, the way the atoms are bonded and microstructure. And we look at the plate glass, we have around about 9, Mr. Kiefer. As you can see, you compare that to steel, wood is around about 5.4, concrete 10.8. Yeah, just a few of them. It's not that you expected to know. I'll tell you why I'm showing all of this. So if you look at some plastics, plastics obviously have very high thermal coefficient of thermal expansions. You're reaching the magnitude of around 90, 95.4 or in this table. And then you get at your composites, and composites, it's the only thing I find limiting within the current diploma is that we only focus on steels, right? And we can do all the same analysis for other materials. I'm talking about your composites, your plastics, of course your biomaterials. We only use steel because I guess it really is the main material we use within, of course, steel and all its sub friends that we do the analysis for. But if you're gonna, for instance, you're just looking at the one on your right for composites. So composites are anisotropic, which means the properties essentially they differ. The properties differ in different directions. So looking longitudinally, they have a negative thermal. If you look at the Adamant epoxy, they have a negative thermal coefficient of expansion. But if you look at it longitudinally, on the other hand, it behaves completely different. So yeah, it's quite interesting. Different materials will behave differently, and it's obviously to do with the, I would say, all the material science below that, the microstructure, the way the atoms are arranged, etc. So yeah. Note. Okay, so let's get into the nuts and bolts. So back to that NB, right? The main important thing to note, right? So yeah, okay, I'm just reading off here. It says if the ends are rigidly fixed, then the change in length due to change in temperature is equal to the change in length due to stress induced in the material. What does that all mean? Okay, so the first thing you want to imagine, number A, right? So we've got some bar fixed to something. Who knows why? It is what it is. Right? I don't know who decided, okay, we're just going to fix a random bar against the wall. Maybe Mr. Cassie just welded it there. God knows why. At original temperature, there's no stress induced, obviously, right? So we have 25 degrees ambient, nothing's happening. Let's say maybe starting the engine up, who knows what, and the engine room temperature heats up to 40, let's say 40. So we're from 25 to 40. It's not a big gradient, but it's a gradient nevertheless. So they're saying B is free expansion. So we're just allowing the thing to expand. So what is expanding by is why don't I have the formulas over here? I don't have the basic models which I also want to include. Just give me a second. I'm just having a look here. Yes, I didn't actually include the models here. I thought I had it over here. Yeah, so if we're letting it extend, it'll just extend. However, there's no stress induced. I'm having this small discussion around, around this on this particular note before we move on. And then now let's say, okay, you know what? I don't know what. So Alex decides, okay, he's gonna end up fixing this. He's gonna have two ends fixed, right? So think of it as a fixed cantilever. Just want to set up my tablet here, so I'll just have it show you now what I'm talking about. Where are we here? I just can't believe I didn't have the model. So anyway, the model I was referring to is that the change in length we can determine by using this formula over here. Do I even still remember it? It's alpha LT, right? So if there's an increase in temperature or decrease, that's the formula you use. Obviously, your alpha is your coefficient of thermal expansion, L is the length, T is the temperature, right? So bear with me on that model. So what I mean, original temperature, nothing happens, we're 25 degrees. In the engine room, 40 degrees. But now, let's say we decide to fix the ends, both ends. So when I mean fixed, we are kind of putting it between two supports like this. It's like a bolting beam when caster, right? So if now we increase the temperature from 25 degrees to 40, right? So there's some kind of gradient, let's say non-uniform gradient. This, whatever material it is, it's going to push against this thing. And of course, the wall is going to react. Therefore, a stress is now induced to the magnitude of, it's a mechanical stress, essentially, stress R over E. Okay, so that's for C. I hope everyone gets this. We'll talk about it now. And then on D, just bear with me. So there's a restricted movement. So if we have a bit of an allowance, so if we just having a look at this, so what essential allowance means, there's a bit of play in between the thing. So let's just look here, ends are fixed. So we've got a space, we've got some space for it to kind of what's the word I'm looking for? Extend or elongate. And we're gonna have to account for the allowance. So now I just wanna show you, let me just copy the dead models here because it's really bothering me. I'm not sure why this formula is not here. Where are you? Trotsky. Here we go. In a second. Yeah, got it. Yeah, here we go. Okay, so cut. I'm just gonna get it on the slide here. It's essentially what I'm explaining here, but I'll just recopy so that it's on here. Not sure why is it not. So that case, this is the case where it's fixed, right? That's where it's fixed. And lastly, that's if an allowance is made for restricted movement, right? Okay, so that's the two cases which I was highlighting just now shortly. So it's fixed, there's going to be a stress induced, and of course, even when you have a bit of an allowance, what we're going to have to do, it's exactly the same, but of course, we subtract the allowance. So before I move on here, is everyone clear when the stress is induced? In this context, of course. Students, are we all there? Yeah. Okay. Thank you. Thanks, Sasha. Yeah. Anyone else? I hope you understand, the idea because if I'm feeling good, I can make a scenario where the thing extends, but it doesn't extend. Let's say it doesn't extend all the way, and there might not be any stress induced. So just be aware, But anyway, let's have a look. So okay, so we just have a quick example we're gonna touch on here. And then I'm gonna give you one practice one. Obviously, I want to see if you guys are, all there. You have enough time to kind of cover everything here. So first thing is first. Yeah. So let me do the example. So 25. It's your first. It's your first example since the textbook. I just remember if I'm gonna play around on this one anyway. A 25mm diameter steel rod. Right. So you've got a rod. Let me just create a small rod for you here. Where are your rod? Yeah, it looks like a rod to me. Yep. There we go. Steel. Yeah, it's steel now. Okay. It's 1 meter long and it's clamped on both ends. Right. So there we go. So it's fixed. So did it tell you what's gonna happen? Right. So this could have been a shaft for crying out loud. It's maybe some bearing supports or whatever. And now the temperature is decreased by 60 degrees. Right. So that they're telling you, I guess, the gradient here already. Calculate the stress induced around if the ends were rigidly fixed. Okay, so we know change of length. I guess I'm gonna call it the mechanical change of length. What did we call it last time? It was mechanical. According to what I called the mechanical change of length and the thermal. And obviously we've just done this. It's the form of the models already given to us here. So it's this LT, that there. It's a scale here, and just basically with the stress alpha. Stress equals your coefficient of expansion. I'm just going with a T and an E. So if it's fixed, that's what's going to happen in this one case example. So if you compute that, it's 12 times 60 times 200, which is your elastic modulus. It's always going to be there, and then 44 tensile. Why is it tensile?
Because it's a reduction in temperature.
A reduction. Are we on the same page here? So if the temperature is reducing, shouldn't it contract?
The ends are rigidly fixed, so you're having a tensile force.
Yeah, there we go. Does everyone get that? I'm just checking. Yeah. Okay. Yes, no one is gonna. So.
So I don't get that.
Yeah.
The ends are rigidly fixed, but it's expanding.
Yep.
It's a tensile force. Would that not make it compressive?
So it's fixed, right, and it's contracting, right? So this is why one has to really look at the direction of these forces. Where is my other color? Green.
Oh, so then why is it contracting if we're heating it up?
It says if the temperature of the rod is decreased by 60.
Oh, sorry, it's decreased. Okay, sorry.
Yeah. Are you following now? I'm not sure you're. So, but you'll touch on it. I mean, it's gonna come out. It'll give birth to itself. We'll discuss it now. And obviously when you have an allowance, right? So there's a bit of, I guess, bit of room. So what happens is it's the same model essentially. Well, not really the same because now we have a different change in length. Just bear in mind these are, if you look at all this, these are all meters here. So just making sure that you're aware of this. So if you have a bit of an allowance for the contraction of the rod, it's gonna be well, we have to use this. Well, let me just get that right. Stress L E equals it's the same, I guess. Basically, it's what's it, alpha LT And of course, because it's a bit of space, it's not the same. So we have to subtract this allowance. I'll just call it A for the sake of, because there's a bit of room there now. So we're basically essentially moving that. That's just speaking to this figure over here. The sensors are important. We know, and we're going to get to that sensors now. Because that's what trips everyone up. So that's just looking at from a formula based, but we will start touching, we will start seeing why this is happening. Okay. So what I want you guys to do now is try and do example 2, which is 7.4 in the textbook. And it's basically a steel rod joined to a copper rod. Now, this is a series arrangement. And I just want to see, as I did this last year, and I want to see if you guys are able to kind of figure this out. So now we have an increasing temperature. Now, what's important is we're really going to start to see because the sensors playing around with each other. So try and do this one, and then obviously we'll touch on. I'll solve this one, and then we're going to move on to actual series. So yeah. So I'll give you guys around, I think 10 minutes should be enough. So if you do want to maybe get some hints, obviously it's just, like I said, it's a series arrangement. But I'd like to see if you do understand the sensors though. That's where I want to. That's where I essentially want to get to, because yeah, you've got two shapes. So you've got two rods here. Just see what you can do, right? In this case now, this will give me, obviously just assume that they're both fixed. One is copper, one is steel, I think, and they're both fixed, right? Now it's going to be very interesting to see now, because one is going to be here we go, fixed, or one's going to extend faster than the other one. So I want to see exactly if you guys can pick it up. Okay, guys. So just yeah, around half past we can actually just get back to this problem. So try and do this one. What's important is look at the sensors. I want to see if you guys can pick up the sensors within the thing. Okay.
Sorry, sir. Can you just go back to where the formulas were?
Yeah, it's do you have a textbook?
Not just yet.
Yeah, because it's these formulas are not gonna like particularly help you with this problem, and that's the thing. So I want to yeah, it's those are the formulas, but yeah, you're gonna have to someone's gonna have to take a picture of the formulas for you. Where was I now? There's 2 bars now, so I want to see if you're able to kind of interpret exactly what's gonna happen. Do you have the formulas down there? What example are we doing now? 7.4. Is it done? Are you done?
Yes, thank you.
Okay, cool.
So is there a tensile stress in steel and a compressive stress in copper?
Now you're talking. It says they're both are compressor there. But now you're talking. So I agree with Alex there, but why does a book have both compressive as, and does anyone follow that train of thought?
I think so because copper's got a greater temperature coefficient, so it would expand more readily than steel. So
That is correct.
there will be a compressive stress in copper when it expands, but it will also be, because it expands more readily than steel, it will be inducing a compressive stress in steel as well, because it will be forcing. But my understanding was that because steel has a lower temperature coefficient, the copper it would actually be more intense stress because it doesn't expand as readily as copper.
That is correct. This is what I thought. So I'm finding it quite strange. I don't know exactly why.
Can I add to that?
Yeah, go for it. Yeah.
They are both compressive. They are not, one's not in tensile and compressive. Because they both expand and the ends are rigidly fixed, they are both incompressive. The compressivity of one is more than the other one if you think of it in terms of a force, but in terms of stress, it's irrelevant.
Okay, but Ingo, can you please elaborate more? I see what you're saying, but let's start it. Yeah, just talk to it because I'm on Alex's train of thought.
Do you want me to solve it for you?
Yeah, no, go for it. Yeah.
Okay, so what I did is you take the total change in length. If you were to imagine that, let's say for example, the ends were rigidly fixed, right? So
That's
you
correct.
do like
Yeah.
a free diagram. So the change in length of the steel and the copper you work out. So then you're going to get a total change in length of the composite bar together is going to give you
That's correct.
292 times 10 to the power negative 6 meters, right? Then the second step after that, because it's in series, you take it as if you were to convert that change in length due to a force, then you'd say
Yes.
that the stress of the steel times the area of the steel is going to equal the stress of the copper times the area of the copper. But because the
Yep.
areas are the same, that means the stress of the steel is going to equal the stress of the copper. Then, as I've already worked out the total change in length due to the temperature, what you then say is you say the change in length is going to be equal the
Yes.
stress of the steel times the length of the steel divided by the modulus of elasticity of the steel. Then you're going to
Yeah.
add that to the stress of the copper times the length of the copper divided by the modulus of elasticity of the copper. But because the stress of the steel is equal to the stress of the copper due to the areas being the same, you then just work out whichever one you want, and that will give you your stress.
Okay. So that is very good. That is very good. Yeah. Okay. Okay. Right. So is anyone
I can screenshot the working out and send it if you'd like.
Yeah, you can do that on the group. Yeah, no problem. I was gonna work it out anyway, but it's fine. You can do that. Can you guys hear me? I think my mic's busy. Like it's showing a loading sign here. Go for it, yeah.
Yeah, I pretty much did exactly the same way as what Sasha did.
Yeah. Okay, no, that's the same phone audio. Okay, cool. Now, yeah, you can send it to us, Sasha. That'll be great. I think why it works out quite nice is the areas are the same. So let's see. Okay, I'll solve it anyway. The sensors are the tricky one here in this particular chapter. It can be confusing for a lot of students. Okay, cool. Take this.
Yeah, I just dropped it in the group. Excuse my handwriting. I'm doing it on my iPad.
That's cool. We'll have a look now. Shade. Okay. Just give me a minute here. Yes, Sasha, I've received it. I'm just give me a minute. I saw something. All right. Where are we here? Where's my whiteboard? Okay. So first thing is first, right? Because it's a series arrangement, I think what I was trying to really pick up here before the sensors, right? Both these materials are going to expand. All right. And so the normal, well, the standard model of our series arrangement looks like. Let me just get this right here. The forces are the same, right? So yeah, the forces are the force in the first one, the same as the second one, and therefore we can do this kind of setup over here, right? Stress 2, right? So this is what I was trying to. Then of course, because it's in series, they all have individual change of lengths. I think that's what's important here. Okay. And then of course L1 plus L2. This is something you're familiar with. Obviously, this is kind of not what you're used to, but in the temperature stress context, I guess. This is the way you want to view this. And this total change in length is due to thermal expansion. So you should be aware of that here. Okay, so just following the way Sasha did it here. Well, I think we all did it the same way. Can do the same way. We have to work at the total change in length of this arrangement here, right? So steel was 120 long. This was 80 long. Diameter here was 20, and the copper rod 20 diameter, about 20 diameter here. Yeah, okay, cool. The same area. Yeah, forgot about that. Okay, cool. So it's stress L T steel plus stress L alpha. So that should get you total. So steel was normally, well, this is 11 in this case, not 12. Length, what is our length? It's of the individual one, so that's 120. The cables are increase of 100. We could obviously just take out a common factor here, but it's okay. So what did we get for this one? It's not. I'm just probably have a look at session one afterwards. What did you guys get for this one?
The change in length, sir?
Yeah, the total. Yeah, that's correct. Yeah.
0.292 millimeters.
0.292 millimeters. Millimeters times 10 to the -3 or what? Straight
Yeah,
millimeters.
times 10 to the -3 meters, so it's millimeters.
Yeah, millimeters. Yeah, okay. Yeah. Cool. Fine. Right. So once we're done with that, now remember the areas are the same. Therefore, the stress is the same, and this is why they're going to have the same. They both can have the same. Obviously, the stress of different things could have changed. The same sense and same magnitude of stress. So what we can do now is where are we now? We have the total change in length here, right? And of course that's gonna be here now. So that's 0.292. And this is a very special case, students, just to make you aware. So stress L is steel. I'll repopulate this again. So stress L E copper. Okay, so these values are the same, right? So that's how whatever we get. But I'm going to talk about the sense. So because these are the same, obviously we can just let's say 0.292. Let me just sort it out. I'm taking stress. That stress is a common factor. Length was 0.12 divided by 200 plus what's this guy again? Length 0.08 divided by 100. I think 108. Okay, this is what I want to touch on now. Where are we? Stress in, does it really matter? Let's just call it stress of steel, right? But stress of steel is equal to stress of copper. Okay, so what is that magnitude? Oh, it's obvious the answer there, right? Students, are we all happy with this? Do we all have a feel for what's happening? You've got two bodies extending, but the sensors are at ski over here now. I guess I'm losing people here. Just sorting something on the side as well here. Do we all manage to get the so-called stress in steel? I just want to discuss the sense. Yeah, I'm sure. Alexander, you got it. Did everyone else get it? Yeah, fantastic. Okay, just that you understand what's happening here. Okay, that's going to be, I think, 217. Do you guys get the exact? So now the problem is the sense, either sense positive or negative. Now the thing is, if I'm getting a positive value, I'm assuming this is tensile. This is what's getting to me. I would say steel is tensile, and what is this? Copper is compressive. That would be my train of thought. Because can you please make the pen color or make it a bit thicker? Okay, yeah. Let me change the pen color. Sorry, man. I've just, it's not a conducive. Yeah, it's cool. I hope you can see this here. Okay, I'll just for the next example. But my argument here is that as the copper is extending, right? It's being compressed here, right? That's pushing, that's inducing a copper stress. Whereas this, if you're looking at your, let me just get your, Sasha, can you just go over your thoughts on why this is both compressive? This, to me, that's what that looks like.
They are both compressive because they are both expanding. So if you have to think of them individually, and if you, let's say you took into account that one side was not rigidly fixed, so if they were free to expand, right, you'd have an increase in the change of length due to an increase in temperature of the copper,
That's
and you'd have
correct.
an increase in the change in length due to the steel. But they were fixed.
Yep,
So you have to take both expansions into account. If you were to include
that's correct.
external tensile force, let's say one side was rigidly fixed, but on the other side there was a tensile force being pulled, then you could find that the one was in tension and the one was in compression. But because the ends are rigidly fixed and there's no external forces, they are both in compression.
Ah, I see. So you're saying, are you saying they're both extending, and then the holes are basically just like the holes are essentially squeezing them? Is it cool if I say it like that?
Yeah, the walls are keeping them in place. The only thing that is going to change will be the interface of where the original interface is. That interface will then shift to a new location, obviously depending on the modulus of elasticity of the materials. But they're both in compression. The stress and the force induced are two different things.
The stress and the force induced. Yeah, that's correct.
Yeah, because you can think of it in terms of a change in length, or you can think of it as if there wasn't a change in length, but the same effect would cause the change in length due to a force. If you
Okay, let's see. I like the way you mentioned that there. How do you know if it's tensile? That's what we're trying to figure out here. Okay, so let's try another example. Let's see here. I've touched on this last year already, but anyway, let's see. I know, Miso, you asked me that question. Oh man, what's going on here? Okay, just give me a second here. All right, okay, let's check another example here.
You can actually to try and help understand, you can actually think of it in a thermodynamic principle as well. So if you take it into our industry account, if you have a boiler and you got a steam line and you isolate a steam line, then the temperature drops obviously due to condensation, and you pull a vacuum, which will be a tensile stress on manhole covers and flanges and shit. So it's the reduction in temperature will cause a contraction, which will induce tensile stress.
Oh, I see what you're saying. Like, I see the way you put it. I actually like that. That's a good one. Yeah, I never thought of it like that. Yeah. Yeah, I see. Okay. Let's just quickly see in the next example. So I don't want to confuse people here, man. That's a sport of looking at it. I like it. Okay. So because you just touched on series now, let's just move along. Yeah. So we just did that now, right? So what's important to note, looking at your models there, your statics and compatibility equation. Statics essentially the force, or the equilibrium equation, compatibility to the change in length. So just looking at the diagram over there, let me just increase this size. So you've got two members over there, right? If it's at original temperature, once again, we know that there's no stress, going to free expansion, but of course it means it's not fixed. The length will increase, but there'll be no stress induced. However, if we fix it now, there'll be stresses induced due to it being fixed, right? So now the question is whether it's going to be tensile or compressive. So now I want to make a note. So Sash, you can just repeat the thing, or we talked about force and stress. I actually want to write it down here.
Yeah, so it depends if you're in parallel and series. So if you're in series, then
Series,
generally in series your force, it should be an equal force exerted on both members at
That's
the
correct.
same time. And then
Yes,
if
that's
you're
what
in
that is.
parallel, when you're in parallel, I always equate it to the change in length being the same, because you can have a force, but your force is not going to be equal on all the different members, but your change in length has
Yeah.
to be the same if the
No,
ends are
for
originally
sure.
fixed.
I'm not talking about that, man. I'm talking about like the sense, like not the members of series. Like I like what you said about the force and the stress is two different things. So like it can be you get a thermal expand it's contracting, but there's a thermal stress, thermal expansion. That's it up.
Yeah. So
And what about the
basically,
sensors?
so if you take the basics of strength of materials, your stress is equal to force over area, right? So
Yep.
that's why you've got there that your stress times the area, which is equal to a force, right?
Yep.
And you can then, if you were to have a change in length on a single
Yes.
substance or structure,
Yep.
right? That
Yep.
change in length can either be due to temperature, or you can also have that change in length due to a force. But
Yep.
that
That's
change in
correct.
length will be the same. So you equate it in terms
That
of
is
force,
correct.
or you can equate it in terms of temperature. It's up to you.
Yeah. Okay.
And manipulating it the way
Well,
you do it there, manipulating the way you do it will help you solve equations, depending on which approach you want to take.
okay, it's fine. Yeah, no, don't worry. I'm sort of talk to the sensors. Sensors mess people around, but we will have enough practice anyway. So again, if you have restricted movement, what we essentially have there is a bit of an allowance. It's just basically a continuation of the models we did before. Parallel is going to get more interesting. So yeah, but parallel, the forces are still the same, by the way. When you're dealing with when the temperature stress around. Nevertheless, so we've just basically did that. So we've agreed that obviously when you have two members next to each other in series, what happens is that they both extend due to the to the thermal expansion. And if we fix them, what happens is that we get two mechanical stresses induced. Fortunately, we're in the same area, therefore our stresses were the same in this case. And the magnitude is obviously of question, which I'm more really interested in. But let's touch this example. So this is an example in the textbook. I'm going to solve through this one, and then I think I have. Do I have another one here? Yeah, I'm sure I have. Let me just quickly see. Yeah, okay. So let me just quickly share this up. This is where we're going to have a discussion with our sensors. So, which is obviously of critical importance, because you notice you're going to have to be able to compute what's this resultant stresses, and that is what's really what I'm really looking for in this particular chapter. Where am I now? Let me just. Oh shit. The whiteboard. Okay. So I'm quite pleased. A lot of guys have worked their head here, so that's fantastic. Okay, let me just quickly see. Oh man, I'm sitting with problems here. Okay, guys, just give me another minute here. All right, okay, I'm back. Let's see. Okay, just zoom the question here. So a composite rod 320 long and a temperature of 120 degrees consists of 200 millimeters length of aluminium, 50 millimeters in diameter, which will originally to an end of 120 length of steel rod 10 more diameter. So this becomes a bit interesting. We have two different two different rods over here. So we've got a small. Oh, yeah. I've got this. Is that how long is this now? 120. Spins a bit thick, and then it's just a bit bigger copper. It's a bit bigger, like something around. And that length is going to be what? What's the length? Can be equal to 200. So it's a similar setup over here. I'm just going to get this diameters down because the spin is a bit too thick. Aluminium. Oh, it's aluminium and steel, not copper. Okay, forgive me. Yeah. So this is going to be steel is 10, and then aluminium is 15 millimeters. Okay. So in this case, check what happens now. So hey, if the ends of the comps are originally clamped at this temperature to restrict any contraction on cooling, calculate the stress in the aluminium and steel if the temperature drops to 20. So check, now we're contracting, right? So what are we expecting to happen? This is what I want to talk about, right? So I'm just gonna be with me. Obviously, this is not the same thing. So we are contracting now, right? First thing what we're expecting here. Yeah, so there's a drop in temperature. Obviously, there's a drop in temperature, so things are not extending, but they're contracting. So I'd like to know what stress will be induced in the aluminium. So is this what's this? This is the steel and aluminium. Okay. So this is what I want to talk about. Before we actually tackle the problem, what are we expecting to happen? So it's contracting now, right? If this is contracting, that means this is going this way, right? And on the aluminium side, what's happening over here? Just forgive my areas here. I really wanted to have them both thin. Let me just really make them one thinner than the other one. Mr. Demanus, what do you have to say? Here's my. So I'd like to know, what are your thoughts? So it's contracting now. So what's happening? It's not expanding. It's contracting. So what I'm concerned is of the force of the stresses induced, because our equation does not give us the sensors. Anyone?
So if both of them are contracting, then I would say both of them would be experiencing a tensile force.
Beautiful. Now, you get it? Can you explain it to everyone?
Yes. I would assume because when as it cools, it contracts, and both members are contracting. The contraction of one will actually provide a tensile force to the other one.
Yes, that's correct over there. Like similarly over here.
Yeah.
The way I always viewed is that the sense, and this is what I liked what Sasha was saying about the sense of the force. I don't know if you meant that, but like if you're contracting, right, and I mean just looking based on the wall, that means it's a tensile stress. It's like the opposite of what's actually happening. So as you're contracting in this case, the force induces now, and we revisit the old example and then have comparisons between the two. If you notice that the previous example, let me just get it right. What was happening? Where are we? There was an increase in temperature, and that is why it was being compressed. So this is what it's like. Yeah, let's have a look. So let's follow the same train of thought. So the way I normally teach it is that I look at the ends of the system, and of course this is in the series arrangement. As it's contracting, I guess there's a tensile force, but you have to look at the whole. Obviously, the holes now, or the fixed end. That's the force, or the sense of the force. But anyway, so first things first, in series we have F1 equals F2, and then we can just do our standard. Yeah, I wanted to do something here as well. I think it's going to work out quite nicely. Stress in steel, area steel. Ah, man, I should have just done this. Stress in aluminium. So stress aluminium, area aluminium. I want to just do that. I just want to have it like this. Okay, so just forgive me with this here. So we're obviously looking for these stresses now. And stress in steel, what's the area over here? Area of steel was pi over 4, 0.01 squared. Stress in what's this other one? Aluminium is pi over 4 times, what is it? 0.115. Okay, so what do we get here?
Stress of the steel is 9/4 the stress of the aluminium.
9/4. Okay. Students, are we all happy with this? Do you all understand what's going on over here? Okay, so
Yeah.
okay, equation number 1. Yeah. So yeah, we'll touch on that and we have a break it in. We'll want some time in this example, obviously. Next, obviously, is our compatibility equation with the change in lengths. So that's obviously going to be simple. That's obviously where this tensile stress induced here. So this is steel. This is going to be aluminium. And okay, so of course a total change in length. Remember, in this case, it's due to the thermal expansion, of course, which induced these mechanical extension or mechanical strains or mechanical change in length. So you've got 0.12. Its coefficient of expansion, thermal expansion is 12 times 10⁻⁶ times 100. We've got to take 100 as a common factor. We've got 0.2 here times 23. Yeah, my students. All right, so once this is done, you should get 0.6043 times 10 to negative 3. You guys all concur with this. Now, the other thing I want to do now is just find, can I just have this as is? So the length of the modulus, can I have that value? Plus the aluminium as well. I'll show you what I'm going to do. So can I have that? The length over there, length of a modulus, length of a modulus. Can we get that quickly?
So I think so. For your steel, that's stress steel, right? So in brackets there would be where did I put it now?
Yeah, I'm gonna do something. I'll show you guys like what I like.
Oh, wait a second. I referred it to aluminium because I got the ratio. So I put the.
Okay, cool. It's fine. That's fine. Okay, so let me just work it out. So the length of steel, you just confirm with me here. It's 0.12 divided by what was 200. So it's 625 times 10 to the negative 15. Just confirm that, please. 15, eh? 15. That's what I have to see here. And then what's the next length is 200, so that's 0.2 divided by 100 or 70, so that's aluminum, it's not copper. And we should get, I have to keep it, so it's 2,857 times 10 to the negative 12. Okay, this really has to be cleaned up over here. And that equals to that. Okay, so what I started doing, to make you all big boys and big girls, just pull a matrix instead of doing all substitutions. So that's equation number 2. What we simply do here is a stress of steel minus 9/4, or 2.25, if I'm correct. Stress of copper equals 0. So stress of steel minus, not stress of steel, man. So this is going to be 1 minus 9/4. This is 625 times 10 to the power negative 15. That's 2,857 times 10 to the negative 12. Just bear with me there. This will be the stress of steel, that will be the stress of copper. This is equal to 0, and this is equal to 0.604 times 10 to the negative 3. Can you guys quickly gooi the stress of steel and the stress of copper for me?
I didn't do the maths the same way you did, but stress of steel is 323,022 megapascals.
Yeah, I'm sure the math, I'm showing you guys some new tricks here. Yep.
And the stress of the
tensile,
aluminium.
right? Yep.
Yeah, and the stress of the aluminium is 143.565 megapascals.
143.565. You see that? Okay. So I'm gonna give a moment to everyone to do that. Yeah, no, Mr. Egelbrecht, I appreciate your expertise here and your enthusiasm today. You're not always here, but I'm gonna discuss now the sensors now. That's what I'm gonna touch on now. That's what gets everyone. But I'm just showing you an alternative. Well, I guess my modern approach. I can't be doing substitution. I'm not a big fan of it anymore. It's too. So, is there any questions on this, guys? Before we touch on the sensors now. Oh, let's first finish up the question before we actually get to the sensors. I forgot there's a whole list of other. Is there any questions still here? Students, please ask. It's okay to be confused. Guess no one's going to say anything. Okay, maybe I should just touch on the sensors now. Let's just do it now over here. So, in series, right? Maybe we should make a small what is this? A small note on this. If this, we had expansion last time, right? If this expands, right? If this pushes outwards, maybe I should use, what color is good here? Something very obvious. If that expands, the wall is going to induce a compressive stress. Students, do you agree? Is that the idea we're looking at here, right? Are we expanding here? Or the previous example we expanded, right?
Yes, sir.
Does it make sense? Yeah, this is what I'm checking. If you're looking at it right. This is what Sash was saying about it's contracts, but there's a thermal stress. This is what I want to kind of get out here. Let's do the other scenario. Where's my pen? Yeah. Hey man. Hey. All right. So consistent. Now in this case, so we had expansion here, right? Therefore, compressive stress was induced. But in this case, we had contraction, if I'm correct. Hey, sorry about that. We had contraction on cooling. So this contracting, my green arrows look like this now, right? And I normally look at the wall, and obviously have to apply the opposite force, and that would be tensile. Misho, did I answer your question? This is for series, guys, right? This is for series. So contraction. Tensile stress. Are you happy? I don't know. You're just saying ES. I don't know if that's a new. The Kiefer, do you have any? Do you get it, Mr. Pereira?
Yeah, I'm with it. It's not really that confusing, to be honest.
Yeah, it's not. Yeah, just that it has happened. Trust me, you'll see. So we just keep it forward in series. Silas, go for it.
Yeah. So you see when you are taking the sense, are you looking on the wall or are you looking at the components themselves?
The whole. The sense is the whole.
Now, so you're looking at what the component will experience.
Experience. Thank you. So
You're
let's.
looking at what it will experience.
Yeah. So the component will experience. I'm gonna create a note on this, guys. But you know this so this is what is experienced. So let's just say induced. Yeah. Component experienced. This is, so what can we call this? The context, right? I don't know. I'm going to call it the context. Yeah. So it's the component wall. Okay. That's fine. I think you all get it. I need to make a note on this. Anyway, this is the fun part. And now I have to calculate the final junction of the position between the two materials after the drop in temperature, right? So, let's go to the Dr. Engelbrecht. So so what did your approach be? Because we can put both ways, by the way. Yeah.
Yeah, so you can either take it into consideration from steel, aluminium. So
here we go. Yeah.
Whichever one you're going to take, then it's a two-step process. So basically, take it as if there was no limiting factors, in other words, no wall, and it was just free to expand. Then you'd work out the change in length for free expansion.
Yes.
But then you got to take into account that there is a tensile force on the system, right? Because you've already worked out your tensile stress, and then the tensile will obviously be a reduction, right? And then you get another measurement there. So you take your free and your tensile and you add it together, and it's going to give you your interface. But take into account that your free expansion is going to be negative because it's contracting, and the tensile force is going to be due to the steel. Yeah, so that's going to be a positive. So you're going to say minus the tensile, and then the addition of the what you call it, the stress of the steel, and then you're going to get your interface change. But you can do it either from stress or from aluminium.
Yeah, so we're gonna do that now, right? So let's go as the book goes, aluminium. That's exactly what I want to hear. Yeah. So the aluminium, what we're gonna do now, so we could have done this for the previous example as well. Obviously, it was a bit more easier. We assume we can contract freely, right? Like due to just this, so I'm just gonna spare me, guys. Where's my L? Okay, stay, right? So this is for aluminium. So I'm going to say consider aluminium. Yeah, so should be consider aluminium. AL. So we first step is we assume it to nicely expand freely, but of course this is not expanding freely, it's contracting freely rather. So the sense would be negative. Well, let's see. So let me just get these values again. It's 23 and 70. Okay. So 23 times 10 to negative 6. What is the length again? 0.2, 200 millimeters, and then our temperature is 100. Okay. So I think I'm going to call this negative, right?
460.
460 on the dot. Okay.
460 times 10 to the minus 6.
Oh man, it just happened again now. It's just, give in here, it's like it's doing something. I don't know what it is. Let me just go check here. It just decided to give up on me. Man. Wait. It's my mouse. Where's my mouse? Okay, I'm sure you guys can still hear me. Let me just go see what's happening. And we got these new laptops and it just decides to freeze on me. Yeah. Okay, let me just reset this and get back quickly. Give me like 3 minutes.
Start from the bottom. Shake that ass, do something, hoes. Black back in the house, start frontin', yo. G straight from the back. Just shake that ass for the splash.
I'm not sure what happens to me, but yeah, it happens. Bet 460. Can you guys hear me?
Yes, sir. Yes.
Okay, thank you, guys. Let me see if I'm recording here. That's it. I don't know if your Blackboard is stable on your side, but mine's like reconnecting. Okay. Anyway, I'm back. So 460. Let's just get my graphics tablet back in here. Times 10 to the -6 on -3. So you can actually see it's a small expansion there. Meters. All right. But we've got a mechanical stress induced. So of course this is going to be negative because it's contracting. I'm gonna make that blue, or no, not blue, make it red rather. Hey. Okay. Guys, I'm assuming you guys can hear me. Just 1 or 2 students. So what is the component experiencing? That's a tensile stress, and that's gonna be stress LE, and we found the stressing steel to be what's it? so it's the aluminium, sorry. So that's going to be 143,565 times 10 to the 6. Length was 0.2, and that's 70. Of course, this is going to be positive now. All right. Okay. So what do you guys get for that for the tensile induced stress?
410.186.
410.1.
86. Yeah,
19. Okay.
Times 10 to the
965.
minus 6.
Yeah. Okay, meters. Now the sense is positive. There we. Okay. So all we essentially do now is just gonna have to add this up to show how much you contract. So therefore we just add them together. I guess you'd say now total change in length of the aluminium is going to be minus 460 times 10 to the negative 3 plus 410 times 10, of course, 186. And of course, we're going to get a negative, I think, negative 49 something, 49.814. Do you all concur with this answer? Are we happy with it? So what this means is it's contracted by that much. All right. Are we happy with this? But we're not done yet. They've requested.
Yeah, I'm happy. I just made it that there were positive values, but if there's a temperature decrease, you minus 2 values, and if there's a temperature increase, you add the 2 values.
Increase. No, it's the same, right? I'm just doing that way. It's perfectly fine, yeah. So the final junction, so that means basically we have to account for the initial length. Yeah, we're gonna have to kind of close this off. So it'll be the total length. It'll just be the 200 minus that, yeah. So it's 200 or 0.2 rather. That'll be the final junction. 0.2 minus 49.814 times 10 to the negative 6, and it'll be 199.95 millimeters from the aluminium end, right? Okay, so what we're going to do now, we're going to do for steel, and we expect it to get exactly the same answers, right? So let's draw a line here, and you just quickly confirm. If you have time to check, this is what to check. So once again, we're considering steel, but we're allowed to expand freely, so to say, or contract freely. And what is my 12? And then my length was for steel. What is my length for steel? 0.12 at 100 degrees. Yep.
So is that 49.814 a gap between the aluminium and the steel?
Can you just repeat that again?
That 49.814 times 10 to the minus 6. Is that a gap between the aluminium and the steel?
Yes. Arguably so.
I thought they were like welded together or something. I thought they were like literally fixed together to make one composite rod. I didn't think they were just two individual.
Yes, not a gap, but like. Let me find the words here.
The composite rod is a rod, a single rod of two different components, so they're fixed together. It's not a gap between them. So on the original rod, they gave you the dimensions of each rod, and obviously due to them both rods being of dissimilar metals and they have different modulus of elasticities, the change in length for each one will be different, but they're still joined together. That distance that you were talking about there is where the original distance has shifted to.
Yeah, that's good enough. So it's not like there's a gap. It's a mistake what I said there. Okay, but anyway, let's just do for steel here. Steel is contract. We're allowed to go. So what's my change in length of thermal expansion there? Can we just get that value? I get 144, right? And of course, we know this is contracting as well. I'm just checking my lengths here. Just this was one length was 120. Yeah, it's 120. And other one was 200. Okay, it's making sure. Okay, once we're done with that, we can do the. This is now the mechanical case stress, and our stress here was. Let me have a look. It's 323.023 times the length. 0.12, and that's divided by 200. All right. Can someone just hit me with that one quickly? Total. Mr. Mart?
193.81 times 10 to the minus 6.
Thank you, Mr. Kasser. And we can do the same kind of thing. Of course, you can do it like Mr. Kasser, you can just subtract the end, or you just do it like this. I'll just, obviously, we know it's contracting over here. Is it -6? What is this guy? Plus 193. That's tensile, so this becomes positive. Times 10 to -6. What's this one? It's 114 plus 193.81. Then we should get the exact same answer. No, of course, it's negative. Students, are you okay with this? If you ever get a serious problem, you shouldn't have a problem at all. Then I think just recapping on the new position here. Let's see. Oh yeah, then of course, if you do it from this end, we can actually work out the length as well. So is there any questions finding the change in length in both materials? I think people are all. Yes, Alex.
I wouldn't have a question really of the change in length, but I just have one question, just considering last semester when you were doing what's the name, yield stress. What happens if the temperature of, for instance, is raised to the point where the induced stress is greater than your yield stress?
There we go. Those are things I want to touch on in the other bulk example. Yes, it'll fail. It's all within the same laws. So if we're considering, for instance, let me quickly throw this up. A classical question what I might ask is, assuming, obviously, in this question, they have not gave us any allowable stresses. So I'm just gonna, going off the cuff here, let me just go back to, I don't have a table here. Yeah, let's look at steel around 3 to 5, and what's my aluminium? It doesn't have a particular yield, like also 3 to 5 and 365. If normally if I give an allowable stress, so I'll say assume the steel has a, so obviously we're at 100 degrees here. So if I say this is now going to be, the steel has an allowable stress of 355. That's a standard ST55 steel, and aluminium doesn't particularly have a yield, but we can call it 300, right? And if we push up the temperature, right, to in this case, what do we push it up to? Yeah, to maybe like 150 degrees. And obviously, if this exceeds that value, then the component will break. So definitely. So yeah, we will touch on something like that. But is everyone happy with this? Because we will take a break and then we'll start on parallel. Then you basically at the end there. Is there any questions, students? Any questions, people? Please don't sit there and not ask a question. This is the time. I guess it's Monday. Yeah, Sasha, go for it.
That funky maths you were doing at point, can you explain that?
The maths, the matrices.
Yeah, the matrices. I don't know how to do that.
Okay, cool. No, that's fine. I'm happy that you asked him a question. So, yeah. So, since like last semester, I was encouraging a lot of my students. Always when you're sitting with with Bayesian simultaneous equation, right? Or two equations, two unknowns. You're aware of that. So what I try to encourage is to use matrices to actually solve that. So if you look at this, essentially what always when we're substituting, right? We always when you're substituting, we actually have two equations, two unknowns. So obviously the two unknowns in this case would be the stress of steel and the stress of copper. That's the one equation when we do the static so-called equation, the force equation. And when you come to the change length or compatibility equation, we essentially end up with the same thing over there, right? So we have two unknowns, which is just going to be the stress in steel and stress in aluminium. So the reason why I encourage it, obviously, is because we make less mistakes by substitution. Some guys like the old way, but I prefer myself personally, which I just showed you. You can substitute, do not be faulted on that. You just set up two equations when you see two equations, two unknowns. Obviously, you can do exactly the same with three equations, three unknowns. So in this case, and you're going to have obviously your two forces equal to each other. You get that ratio. Obviously, you're bringing the 9/4 onto the one side to get an equation equal to 0, because you want it to kind of follow the same thing in terms of stress of steel minus stress of copper, or stress in copper. It's exactly the stress in aluminium. I keep on saying, see, this is yeah. So do exactly the same, obviously, with your changing length or compatibility equation. You have that over there. Boom. And then what I encourage now, so just have to bear it, but you're going to have to read me these values, because I'm going to have to share my calculator. The reason why I also showed is that I can potentially make problems more complicated like this. So that, and you guys also have more modern ways of and smarter ways of actually using linear algebra or matrices to solve problems. So Sasha, I'd go if you have this calculator, I did encourage you to buy it, I think, mode, equation. And of course, here you have your first one is your 2x2 and your 3x3. So I just choose number 1. So I choose those coefficients. I think the first one is 1, stress of steel. Other one is minus, what's it? Is it 9 or what's it? 9/4. Let's just have a look here quickly. 9/4. It is equal to 0, so that will be your C value. And then this guy would be your 6 to 5 times, what's it now again? Can I just type in E here? I have to use mouse with engineering notation. No, not engineering. Oh, times 10 to negative what is it again? Negative 15, right? Yep. That was negative 15. Others 2,857, 2,857. And that's gonna be negative. What? It's just can't recall that one. Was it negative 12? I think. Yeah. And that was equal to the total change in length of 0,0604 times. I think that is correct. I will just go equal. I should get my answer there. We should get. Well, that's. I'm not sure the answer doesn't look right now, but I mean, obviously, I've probably messed up with some of these values. But that's the idea. Then you get the one value, you get the other one. Oh. Yeah, so I probably messed around with these values here. So just forgive me. Are you happy with that?
Yeah, that's cool. Thanks.
You get it? Yeah, that's all. But basically, yeah. Is there any other questions?
Sir, I want to know.
Yes, here we go.
How do you know between the X and Y which value is for what? Because I'm confused there. Could you please explain?
In the calculator.
Yes, after I get the final result, the X and Y values, which one is for which one?
Yeah, so it depends. It depends on what you put in your matrix. So I'll just quickly show you on the board. Like I said, you can use whatever method you really want. It's just that I find that easy for myself. I'll show you guys an alternative way of actually using, and also to make problems nice and complicated. So now it says my video quality is low for some other reason. Okay, so X and Y. So if you look in the calculator, let me just get this right. It has X, Y, or X and Y here. So X is whatever you put in first here. So if you put in copper here, and then that becomes X, and if you put in steel, that becomes Y. You get it, Mr. Abril? Well, this is a question.
Oh, yes. Thank you. I see. Thank you.
Yeah, that's all. It's really up to you. As long as you have it in the same order. I mean, and the signs are all right. I mean, that's how it's gonna work. But you can obviously just do your way. I mean, it's not really a problem. Okay, so guys, let's have a tea break. We're gonna come back and then we're gonna push parallel next. And yeah, then we're gonna basically end it off with another example maybe. And then we're done for temperature stresses. So there's a nice big example which I'll probably want to push. And yeah, that's gonna be interesting to do. Just okay, I have the answers over here. So let's come back at 1:45, and then yeah, we'll be done as planned, and then yeah, you guys can go play around with I see some guys are really sharp. They don't need at all experience with this, but yeah, thanks for also participating and sharing the knowledge there, which is great. I like that. Yeah, okay. See you guys at 1:45, 11:45.